Have you ever wondered about the odds of something happening? I don't mean just a gut feeling, but the real, actual mathematical probability. Well, today we're going to decode a super powerful tool for doing exactly that, the binomial distribution.
All right, let's kick things off with a simple question. You flip a coin 10 times. What are the chances you get exactly 5 heads? I mean, it feels like that should be the most common result, right? But what are the actual odds?
So this isn't just some random brain teaser. It's a very specific kind of probability problem. And the good news is, there's a fantastic tool that was literally designed to solve this, and a whole bunch of other problems just like it.
And that brings us to part one, more than a coin toss. Because, while the coin is a perfect starting point, the real power of this idea goes so much further.
Okay, so this tool is called the binomial distribution, and all its power is packed right into that definition. Basically, it lets us figure out the probability of getting a certain number of successes, like our 5 heads, over a fixed number of tries, but only if each try is independent and only has 2 possible outcomes. So, how do we know when we can actually use this thing? Well, it's not a free-for-all. There are some specific rules we have to follow. Let's go through the checklist for what makes a binomial experiment. Here it is, our checklist. First up, you've got to have a fixed number of trials. We call that n. For our coin, that was 10 flips. Simple. Second, each of those trials has to have only 2 outcomes. Think heads or tails, success or failure. And third, and this is crucial, the probability of that success, which we call p, has to be the exact same for every single trial. Now, if you can check all 3 of those boxes, then you get to use this cool statistical shorthand. This little formula just says our variable, x, behaves as a binomial distribution with n trials and a probability of success p. It's just a fancy way of summarizing our setup. All right, now that we've got the rules down, let's get to the engine that makes this whole thing work. In part 3, we are going to decode the binomial formula. Okay, deep breath. Here it is, the formula. Now I know, it looks a little intimidating, like a bunch of alphabet soup. But I promise you, every single piece of this thing has a simple, logical job. We're going to break it down together, piece by piece. And to do that, let's ditch the coin toss and use a real-world example. It's a fact that about 8% of men are colorblind. So let's say we grab a random sample of 10 men. What's the probability that exactly 2 of them are colorblind? In this case, our n is 10 and our probability of success, p, is 0.08. Let's start with our successes. We want exactly 2. The probability of 1 man being colorblind is 0.08. So the chance of 2 of them happening is 0.08 times 0.08, or 0.08 squared. That's the first chunk of our formula done. Of course, if 2 men in our group are successes, that means the other 8 have to be failures. The probability of a single failure, that is, not being colorblind, is 1 minus 0.08, which is 0.92. And since we need 8 of them, we just raise 0.92 to the power of 8. And that's the second piece of our puzzle. But wait, here's the twist. You might think we just multiply those 2 probabilities together and call it a day, but not so fast. Why? Because think about it. The 2 colorblind men could be the first 2 guys we talked to, or the last 2, or one at the beginning and one at the end. The order can change. So the big question is, how many different combinations are there? Get this, the answer is 45. Yep, 45 different ways. And that number comes from the very first part of our formula, that nx thing. It's called the binomial coefficient, but I like to call it the chooser. Its only job is to calculate how many ways we can choose our 2 successes from our 10 trials. And 10 choose 2 is 45. And now, we just put it all together. We take the number of ways it can happen, 45, and multiply that by the probability of our 2 successes, and then by the probability of our 8 failures. The result? There's about a 14.8% chance of finding exactly 2 colorblind men in our sample. See? Not so scary after all. So now that we've totally decoded the formula, let's move into part 4 and talk about actually calculating the odds, especially when the questions get a little bit trickier. What if the question wasn't exactly 2, but at least 2? Well, that means we need the probability of finding 2 or 3 or 4, all the way up to 10. That sounds like a lot of work. Now, we could do this the long way, calculate the probability for 2, then for 3, then 4, and so on, all the way to 10, and then add them all up. Or we can work smart, not hard. The probability of at least 2 is just 100% minus the probability of the only things we don't want, which in this case is finding 0 or just 1.
So all we have to do is quickly calculate the probability for 0 successes and for 1 success, add them together, and subtract that total from 1. It is way faster, and it gives us our answer, about an 18.8% chance.
And hey, here's another cool thing. The binomial distribution also gives us some awesome little shortcut formulas. We can find the mean, which is just the average result you'd expect, and the variance, which tells you how spread out the results are likely to be. For our example, the mean is just 10 times 0.08, which is 0.8. Super simple.
Okay, let's bring it all home with the key ideas you really need to remember.
So, what's the bottom line here? First, remember those 3 rules: fixed trials, only 2 outcomes, and a constant probability of success. Second, remember that handy notation: X behaves as B, N, and P. And most important of all, understand that that big, scary formula is really just 3 simple ideas multiplied together: the number of ways it can happen, the probability of your successes, and the probability of your failures.
You know, once you learn this pattern, because that's really all it is, a pattern, you start to see it pop up everywhere. A baseball player getting hits, the success rate of a new drug in a trial, or even how many of your marketing emails get opened. The logic is always the same. So the real question is, now that you know the pattern, where are you going to see it next?